Welcome to paper 2 from the 2018 A-Level Math series from Pearson Edexcel. Let's crack on. Question number 1, find g of x. We could construct the function g of x, but that's a lot of effort here. It's probably the simplest to just plug 5 into g of x, get an output, take that output and then plug it back into g of x. Plugging 5 in, get 7.5 out, plug 7.5 in, 2 lots of 7.5 plus 5 over 7.5 minus 3. And if we calculate that, it comes out as 20 over 4.5, or if you prefer, 40 over 9, or 3 and 4/9, or the decimal equivalent, what would that be, 3.4 occurring. Any of those is a correct answer. For B, the range of the function, well, plugging in x equals 5 into it, and we'll get 15 over 2 out. We know that from part A. As x gets large, I'm looking at the 2x divided by x is 2. That's going to produce the sort of the lower bound for the function. It's going to tend towards 2, and so the range is going to be between 2 and then less than or equal to 15 over 2 or 7.5. For C, finding the inverse function, you don't have to swap the x's and y's around if you don't want to. I have done here because I know lots of people like looking at it that way. So I start by multiplying both sides by y minus 3 and expanding, and then I'll bring the y's onto the left hand side and the non-y's onto the right hand side. We'll factorise a y out, so y lots of x minus 2. And divide both sides by x minus 2, and we get y equals 3x plus 5 over x minus 2. And we can take the 3x plus 5 over x minus 2, and that will be our inverse function. The domain of the inverse will always be the range of the original function, so the domain is going to be exactly the same as what we got in B, but written as a domain, so 2 is less than x is less than or equal to 7.5. Alright, question number 2. With vectors, you have a choice. You can stick with the ij's and k's, or you can turn them into column vectors. I tend to prefer working with column vectors, so I'm going to call a to b 2 minus 5, 7, just looking at the position vectors of a and b. We want to find the position vector for d. So if we add the vector ab to b, essentially we're adding the same vector bd to b. It will take us from B to D. So I'm going to add together 4, negative 2, 3 to 2, negative 5, 7. And therefore D will be 6, negative 7, 10. Or 6i minus 7j plus 10k if you prefer. For B, we have to find the value of a. It gives us the information that the length of the vector a to c is 4. So the vector a to c, a minus 2, 2, 2. And using the formula for finding the length of a vector, essentially it's just Pythagoras in 3 dimensions. The square root of a minus 2 squared plus 2 squared plus 2 squared. That's going to be equal to 4. So all we need to do now is solve this equation that's in front of us. I start by expanding my a minus 2 squareds and then adding the 2 4s to them. So left hand side simplifies to the square root of a squared minus 4a plus 12. That's going to be equal to 4. Square both sides, the 4 becomes 16 on the right hand side. Subtract 16 from both sides to give us a 3-term quadratic equal to 0. You can use the formula at this point. Because the numbers are quite small, I've actually gone with completing the square. So complete the square, add 8 to both sides, square root, and then because it tells us that a is less than 0, we only take the negative square root for the value of a. Positive 1 would give us a value greater than 0, so a is going to be 2 subtract 2 root 2. Okay, for 3a, disproof. We'll disprove it by a counterexample. So just having a think about numbers that will multiply together to make a square number. I've chosen 2 and 8, square root of 2 times the square root of 8. They're both irrational numbers. Multiply them together, you get the square root of 16, which is of course 4, which is a rational number. That is a counterexample to the statement and therefore disproves it. For BI, we're going to do a little sketch. So we'll have a set of axes, my x and my y axes, modulus function, so we get that sort of familiar V shape, and modulo x plus 3 is going to go there. Probably should have marked on 3, and I should probably marked on minus 3 on the axes. So that's an oversight on my part. There's my modulo x plus 3, and then the other one is modulo of x plus 3. We can see, looking at that, there's two sections to this. For part 2, we can see that when x is greater than or equal to 0, essentially these two lines are the same. It's that right hand section. So modulo of x plus 3 will be equal to modulo of x plus 3. And then to the left hand side of the graph, when x is less than 0, it's quite clear that modulo of x plus 3 is going to be greater than modulo x plus 3. So if they're the same when x is greater than or equal to 0 and one is less than the other when x is less than 0, that is enough to conclude that the statement that they're asking us to explain is true for all real values. The upside down capital A, that's a shorthand for all, it means for all, so I'd read that as all x that is a real number, all real values of x. Question number 4, summing the series. So we are summing between 1 and 16, 3 plus 5r plus 2 to the power of r. So the best way to think about this one is to split them up into 3 different sections. So the first one is just a sum from 1 to 16 of 3. So that is 16 threes added together. And then we're going to have 5 lots of the sum of r from 1 to 16. I've actually taken the 5 out of the front of that summation. And then the last bit, the sum from r equals 1/16 of 2 to the power of r. That's going to be a geometric series there. Okay, so calculating each bit separately, well, 3 16s added together is 3 times 16. And then 5 lots, the sum of the natural numbers from 1 to 16, 16 times 17 over 2. There are a number of ways of doing that. I've gone with a simple one, and then for the geometric sequence, r is 2, a is 2. And there's our complete calculation. I've calculated each bit separately and add them together. You can actually brute force this one. There's only 16 terms in the series. If you've just plugged them all in, added them all up, and pressed the correct buttons on your calculator, you'd also got 131,798. Perfectly legitimate. For part 2, the sequence itself goes 2/3 and then it's the reciprocal each time, so 2/3, 3/2, 2/3, 3/2, etc, etc, etc. So calculating the sum of the first 100 terms of this sequence, we can just slice it into 2 separate parts. We've got the 2/3. If we just group all of those together, there's going to be 50 of them, and then the 3/2s, we can group those together, there's going to be 50 of those, and so do 50 lots of 2/3, 50 lots of 3/2, add them together, it gives us 325/3, or anything equivalent to that. Question number 5 is the Newton-Raphson method. So part A wants us to construct an iterative formula that will help us find the solutions. So jumping to the formula booklet, you get xn plus 1 is equal to xn minus f of xn divided by f dash of xn. That's the formula for Newton-Raphson. So f of x in this case is going to be 2x cubed plus x squared minus 1. And I'm going to differentiate that. F dash of x, 6x squared plus 2x. So our iterative formula xn plus 1 equals xn minus, and then f of x over f dash of x. Okay, so the challenge with this question is to bring it together as a single fraction. To do that, I'm going to rewrite xn as a fraction over 6xn squared plus 2xn. So essentially multiplying the top and the bottom by 6n squared plus 2 lots of xn with my xn at the very front, and then I'm going to leave the second fraction unchanged. Then we can take the first fraction and expand the numerator. We already have a common denominator now, so we're going to expand the numerator. I could expand the numerator and join these together. The most common mistake will be in this next step, where we need to subtract the second fraction from the first fraction, subtract the numerators, because you're subtracting each component of the second fraction. So it's a bit of a subtraction minefield here. You're subtracting 2n cubed, you're subtracting the plus xn squared, and then you're subtracting the negative 1 at the end. So we can do this carefully. So we've got 6n cubed take away 6xn cubed take away 2xn cubed. Be the first part, which is 4xn cubed, and then we'll have 2xn squared subtract xn squared is plus xn squared, and then we're subtracting negative 1, so that's a plus 1 at the end, and that's still over 6n squared plus 2xn. For part B, we need to work out the second and the third iterations here. So x2 will be, we're plugging in x1, which is 1, into our iterative formula. So 4 lots of 1 cubed plus 1 squared plus 1, all over 6 lots of 1 squared plus 2 lots of 1. And because we're dealing with ones here, that's a straightforward calculation. It's going to be 6 over 8, simplifies to 3 over 4. To find x3, we therefore need to take 3/4 and substitute it back into the iterative formula. So x3 will be 4 lots of 3/4 cubed plus 3/4 squared plus 1, all over 6 lots of 3/4 squared plus 2 lots of 3/4. For this one, I recommend plugging it into a calculator. It comes out as 2/3 if you've managed to do it correctly. For C, it asks us why x1 being 0 is not going to work. The Newton-Raphson method requires the gradient we're dividing by in the f dash of xn. It requires that to be a legitimate calculation. Now x equals 0 is a stationary point, so the gradient is 0. So the iterative formula would involve dividing by 0, which would not work, would be undefined, so we can't use x equals 0 as its stationary point. Question 6, so calculating f of 2, plugging 2 into the cubic. If you do that carefully, you will get 0 out. At that point, it doesn't ask us to show it, but at that point it's telling us that x minus 2, the linear expression x minus 2, is going to be a factor of our cubic because f of 2 is 0. And that's going to help us with part 2. Okay, for part 2, you can do long division here. If you want to do long division, I'm just going to factorize out x minus 2 from the cubic. Each step involves thinking about a couple of things and working ahead. Easier to do it this way, I'd suggest, although some people really don't like it. Some people much prefer to carry out the long division. If you like a sort of a methodological way, systematic way of doing it, then long division is absolutely fine. Either way, x minus 2 lots of minus 3x squared plus 2x minus 5. For B, they're giving us an equation where they've taken the original function, they've obviously swapped x for y squared. So what I'm going to do is reverse it. So I'm going to let y squared equals x and then carry out a substitution. It reduces the equation down into a cubic again. That should say minus 3x cubed, not minus 3x squared. Well done for those of you who enjoy going through my papers and spotting mistakes, if you spotted that one. And we know that factorizes from part 2 to x minus 2, lots of minus 3x squared plus 2x minus 5. We can read off one solution there for x equals 2. We'll reverse that one in a second. And then any solutions from the quadratic, well, actually there's a hint in the question. It says that there are exactly 2 real solutions. I'm actually not expecting to find any from this. If I calculate the discriminant, b squared minus 4ac of the quadratic, we get negative 56, which is significant because it's less than 0. And that implies that there are no real solutions coming out of that quadratic. The only solutions will come from x equals 2. Reversing the substitution, if x is equal to 2, so therefore y squared will be equal to 2. And we can work out that y is therefore plus or minus the square root of 2. Now the question wanted us to prove there are exactly 2 solutions. Well, we found them both, and so therefore we can conclude that there are exactly 2 real solutions and go a step further and state them as being positive and negative root 2. For part C, this is a different sort of substitution. They're substituting x for tan theta. So replacing x with tan theta, we can conclude very quickly that tan theta must be equal to 2, exactly the same logic as before, and therefore inverse tan of 2 is 1.107 in radians.
Because it's tan, it's periodic every pi, so we can add lots of pi onto that to get within the range. Now you can go and work out all of the solutions by continually adding pi. Even at this stage, you can even look at 7 pi to 10 pi and work out why there's got to be 3 solutions within that range without even knowing them. A number of ways of doing it, but there are going to be 3. If you found them, that's absolutely fine. Okay, question 7, part I wants us to solve a trig equation in the range of 0 to pi over 2. And it's for sine x equals sec x. We know sec x is 1 over cos x. So replacing sec x with 1 over cos x, I'm going to multiply both sides by cos x. I'm going to sneakily split a 2 off at the front because it gives us the clear identity 2 sine x cos x there, which we can replace with 2 sine 2x equals 1. Divide by 2, and we get sine of 2x is equal to a half. Inverse sine of a half gives us pi over 6, and then subtracting pi over 6 from pi to get the other solution will give me 5 pi over 6. Those are 2 values for 2x, so to find the values of x, I'll half both of them, pi over 12 and 5 pi over 12, and any other solution will be outside the range. For part 2, we've got a subtraction of a sine theta and a cos theta. Now, there's a few different ways of doing these. I'm going to walk you through one of them. Some teachers prefer teaching some way, some teachers prefer teaching others. Any of them that are legitimate and correct will end up in the same place. Okay, to show you what I'm doing here, I'm going to do an expansion of r sine theta plus alpha. Theta's the same theta as in the question, alpha's just going to be a constant. And we're going to work out what r and what alpha, what those both are. To help you see where this comes from, I wouldn't necessarily always write this particular line out, but it's quite a nice visual to see what's going on underneath. I'm going to write r cos alpha sine theta and r sine alpha cos theta directly below the 5 sine theta minus 5 cos theta, so that the sine thetas and the cos thetas match up. And we can see, therefore, that we've got the 5 being an r cos theta and the minus 5 being an r alpha, and the minus 5 being an r sine alpha. Using cos squared plus sine squared equals 1, we can actually do Pythagoras on our 2 values to find the value of r. And that comes out as root 50. And then using the sine alpha, so root 50 sine alpha, that's r sine alpha, will be equal to negative 5. I use sine because it's an odd function. It tells us whether we're adding or subtracting. And inverse sine of minus 5 over root 50 is negative 45. So alpha in this question is minus 45 degrees. So the equation that we were originally given, we can now rewrite as root 50 sine theta minus 45, and that's equal to 2. Okay, so now we can just unravel the equation to find the solutions, divide both sides by root 50 to begin with, and calculating inverse sine of 2 over root 50 will give us 16.4. To find the other solution, subtract 16.4 from 180 to get 163.6. And lastly, add 45 to both of those. 61.4 degrees and 208.6 degrees are the 2 solutions within the desired range. Question 8, this is projectile motion, but the question is really about quadratics. We have a negative parabola. We know it lands 40 meters away, so the maximum point is going to be halfway between 0 and 40, which is at 20, and that's got a height 12. To construct the equation of this parabola, I'm going to do it in completed square form because we essentially get given the maximum point, so it's quite straightforward to do. The only unknown is the a that's going to go in front of the x minus 20 squared. Well, we know it's going to hit the ground 40 meters away, so we set h as 0 and x is 40, solve the equation, we get a to be 0.03, so my model for this situation, 12 minus 0.03 lots of x minus 20 squared. For b, we're going to solve the equation when we take our model and substitute h for 3. We're going to get two solutions here, one where x is going to be small and one where x is going to be just less than 40. Do a little rearrangement of the equation, divide both sides by 0.03, square root it, and then add 20. The choice comes when it comes to the square rooting. I'm going to take the positive square root because that's going to give me the value of x that we want. If I took the negative square root, is going to give me a very small value of x. It's absolutely fine if you've done that and then you've rejected the solution. But taking the positive square root gives us an x value of 37.32 meters. In part C, well, we're ignoring air resistance is the obvious one. Not much projectile motion happens in a vacuum on Earth, at least. Certainly not outside of a laboratory. So this is quite the oversimplification of projectile motion. Quadratics are good, but not that good. Question number 9, we're proving the differential of cos theta to be minus sine theta. It allows us to use the limit of h tending to 0, sine h over h is 1, and cos h minus 1 over h is 0. So the differentiation from first principles, replacing theta with theta plus a little bit, which we'll call h, then all over theta plus h minus theta. That's the standard setup for all differentiation from first principles. Obviously the thetas in the denominator will cancel, and we've got to do some playing about with our equation. Okay, using cos of a plus b for cos of theta plus h, we'll get cos theta cos h minus sine theta sine h, and then subtract the cos theta at the very end. That's all over h. At this point, we can split this up into two separate parts. So we've got two cos thetas. So we've got cos theta, factorising out of cos theta, it would be timesing by cos h minus 1 for the cos theta at the very end, all over h. I'm going to split that one from the other one, the limit of sine theta sine h over h, because that allows me to use the two pieces of information that they've given us. So sine h over h tends to 1, and cos h minus 1 over h will tend to 0. So the first one, the cos h minus 1 over h, is going to be 0, so we'll get cos theta times 0. And then for the second one, we've got sine theta. The sine h over h will tend to 1, so it will be sine theta times 1, which comes out as minus sine theta. The cos theta disappears, which is what the question wanted. Okay, question 10 are spherical mint with a radius of 5. I'm going to use r, little r for the radius of the mint, and t for time. We'll do the radius in millimeters and the time in minutes. Now it tells us that the rate of decrease of the radius of the mint is inversely proportional to the square of the radius. I'm going to turn that into maths. That's dr by dt, the rate of decrease of the size of the mint, is proportional to 1 over r squared, the square of the radius. Turning that into an equation, dr by dt equals k over r squared. We have a differential equation we're going to solve here, so I'm going to separate the variables, multiply both sides by r squared. I'm going to upset the purists by splitting dr by dt, multiplying both sides by dt, treating it like a fraction. Of course it isn't. And integrating both sides, r squared integrates to r cubed over 3, and k integrates to kt plus a constant. R is 5 when t is 0. Substituting that in, we get c must be equal to 125 over 3. Substitute that back into the equation. R cubed over 3 will be equal to kt plus 125 over 3. At this point, I multiplied everything by 3 just to tidy it up. So r cubed equals 3kt plus 125. Then we know that r equals 3 when t equals 4. So substituting r to be 3 in, t to be 4. And therefore k will be equal to, subtract 125, divide by 12, simplifies to minus 49 over 6. Therefore the equation that links the radius and time will be r cubed equals negative 49 over 2 lots of t plus 125. If you've got the same equation written in a different way, that's absolutely fine. The question doesn't want it in a specific format. So the mint will completely dissolve when the radius is 0, so I'm going to substitute r for 0 for b. Solve the equation, subtract 125, all bring 49 over 2t onto the other side. Solve it, you get t to be 5.102. We've got to turn that into minutes and seconds. A few ways of doing that. I've just taken the decimal part and multiplied it by 60. That gives me 6 seconds. Ignoring the 5 at the front, so it's going to be 5 minutes and 6 seconds. Then limitations of the model. Well, what if the person decides to bite the mint? It's going to change the surface area. So biting the mint would be a perfectly legitimate limitation. And in the mark scheme, it also suggests you can put that there might be some uneven sucking. I don't think that requires any further explanation. We all know what that means. Question number 11, partial fractions. So it gives us the setup for the partial fractions. I am going to multiply both sides of this equivalency by x minus 3 and 1 minus 2x. The x minus 3 is going to cancel on the b, and the 1 minus 2x is going to cancel on the c. So we're left with the numerator from the left-hand side, then a lots of x minus 3, 1 minus 2x, b lots of 1 minus 2x, and c lots of x minus 3. And then we can start choosing some intelligent values for x, because this has to work for all values of x, including when x is equal to 3. Substituting x equals 3 in, the left-hand side is negative 20. We're going to get 1 minus 2 times 3 lots of b. minus 5b. And the a's and the c's will have disappeared, so b is equal to 4 when we solve that. The other sensible value of x is a half. That's going to make our a's and b's disappear. Solve the equation, we'll get c equals negative 2. For our third choice of x, well, we can't choose anything that's going to make b and c disappear but not a. So in that circumstance, I tend to choose 0 because at least it makes calculating the left-hand side more straightforward. When x is 0, we'll get 1 on the left-hand side, and then minus 3a plus b minus 3c. That's nice because we already have b and c calculated, so I can then substitute those two in and solve the equation to get that a equals 3. So all that remains is to now rewrite the fraction 1 plus 11x minus 6x squared all over x minus 3 and 1 minus 2x as the partial fractions. 3 plus 4 over x minus 3 minus 2 over 1 minus 2x. If you've written plus and then minus 2 over 1 minus 2x at the end, that's absolutely fine. Okay, for part B, it asks us to prove that f of x is a decreasing function. For a function to be a decreasing function, its gradient must be negative at every single point on the curve. So it's not just negative for a bit, it's not negative for, within a range, it is always negative, no matter what, for the function itself to be decreasing. So I'm going to jump straight into the partial fractions version of the fraction because we can differentiate that term by term. I'm going to firstly rewrite them as multiples of powers of each bracket. Allows me to differentiate them one at a time. The 3 will disappear. We'll get minus 1 lots of 4 x minus 3. That will go to minus 2 as the power. And then multiplied by minus 1, also multiplied by the minus 2, this is because we're using the chain rule here. And then we have fully differentiated. I'm going to rewrite them now as fractions again, bringing x minus 3 down as x minus 3 squared, and 1 minus 2x to the minus 2 is 1 minus 2x squared. At this point we could factorise out minus 4. It's quite nice factorising out the minus 4 because everything that is inside the brackets is now quite clearly positive. So we have 1 over a square number plus 1 over a square number. Well, all square numbers will be positive when we're dealing with real numbers. To add a little bit more strength to the argument, I'm stating that I'm aware that x minus 3 squared is always positive, that 1 minus 2x squared is always positive, and so the sum of 1 over both of those will have to be positive too, and therefore when you multiply the positive by negative 4, you're going to get something negative for all x in R. So for all means every single value of x that's a real number, that expression for the gradient is going to be negative. Therefore, f of x is a decreasing function, which is what the question wanted us to show. You could play about with the function a little bit more if you wanted to. There are other ways of writing it which will also demonstrate that it's negative, but that way is sufficient. 12a. This is a trig identity. You always have a choice with proving trig identities. You can start with the left and turn it into the right, or you can start with the right and turn it into the left. I felt that was marginally easier going right to left rather than left to right, although you can do it either way. So I'm starting with tan theta sine 2 theta. Tan theta is sine theta over cos theta. Sine 2 theta is 2 sine theta cos theta. And the cos thetas will therefore cancel. I'll put the 2 at the front, times the sine thetas together, we get 2 sine squared theta. replacing, and all we're going to do now is just rewrite that 2 sine squared theta with 1 minus 2 sine squared theta, because 1 minus 2 sine squared theta is cos 2 theta. That was a case of kind of looking where it's going and seeing what the simplest way of getting there would be. For part B, solving the equation they're giving us, well, the command word here is hence, so hence suggests we're going to use the identity that we proved in A. I'm going to take the right hand side therefore and rewrite 3 tan squared x sine 2x as 3 tan x times tan x sine 2x, because we have an identity for tan x sine 2x. I'm leaving the left hand side entirely alone for now, and I can rewrite the tan x sine 2x on the right hand side with 1 minus cos 2x. That allows us to cancel the 1 minus cos 2x. We would normally have to be careful here in case we're dividing both sides by 0, but within the range that we're looking at here, that's a perfectly legitimate step. So divide both sides by 1 minus cos 2x, and we get sec squared x minus 5 equals 3 tan x. At this point, well, we're going to have to write this as a quadratic in terms of tan x, because otherwise there's not much else we can do. So I'm going to use the trig identity sec squared x equals tan x plus 1, replace the sec squared x with tan x plus 1 to make it tan squared x minus 4 equals 3 tan x. Bring the 3 tan x onto the left and we get a quadratic in terms of tan x we can factorise. Factorises nicely to tan x plus 1 tan x minus 4. And so the two solutions come out from tan x being equal to -1 and tan x equals 4. Apply inverse tan to both of those and we'll get negative pi over 4 or 1.326. We're in radians, of course. Now, the only other solutions we'd get would be adding or subtracting multiples of pi, and that's going to take us outside the range. So those are going to be the only two solutions to the equation within the range. All right, question number 13. So it gives us equation of C, x ln x. First thing I want to do is work out when that's going to be equal to 0. So we get either x being 0, well that's not an interesting solution, or if ln x is equal to 0, then we get the other solution, which is 1, so I'm going to mark the 1 on there. Then I want to find the equation of line L. Well, we know that L is perpendicular to the curve, so I've got to find the gradient of the curve at the point when x equals e. So I'm going to take y equals x ln x and differentiate it using the product rule. Differentiate x, you get 1. Differentiate ln x, you get 1 over x. So the differential will be ln x plus 1. The x times 1 over x will cancel. When x equals e, plug that in, you'll get ln of e, which is 1. 1 plus 1 is 2. So the gradient of the curve at that point is 2. The gradient of the line is the negative reciprocal of 2, so it's negative a half. We can plug now the point e and the gradient negative half into the formula y minus y1 equals mx minus x1. Y minus e equals negative a half x minus e. And from that we can work out that when y is 0, we're looking at the point where L crosses the x-axis now. When y is 0, we can solve the equation and get that x equals 3e. And I'm going to mark 3e onto the graph. Okay, so our region R we're trying to find. Split it up into two sections. We've got the left-hand section. I'm going to drop it basically by dropping a perpendicular down from the point E to the x-axis. The left-hand side of that is going to be an integral between 1 and e of x ln x. That's on the left of that line I've just drawn. Plus, and then we've got a triangle on the right. So the triangle half times its base is going to be the difference between e and 3e, which is 2e, and its height is e. So that triangle on the right is going to be a half times 2e times e. Anyway, back to the left-hand side, we're integrating x ln x. We're going to use integration by parts to do that. I have to pick u to be ln x to keep this simple, because integrating ln x is a little bit trickier. Differentiating ln x 1 over x, we can integrate therefore the x to get x squared over 2. And so the region is uv. So there's my u times v. And then minus the integral of v du dx. Which simplifies nicely to x over 2. And then let's not forget our triangle that we worked out easier. Half times 2e times e is just e squared. So I'll leave that at the end. I'm going to start plugging e in 1. You could do the integral entirely separately and then do it all together if you wanted to. I've started plugging in e and 1 into the u and v bit of it, and then minus the integral of v du dx, so that's going to be x squared over 4. We're going to plug 1 and e into that as well. And don't forget the e squared. So we now have, it's just simplifying and calculating everything is all that remains. So we've got a e squared over 2 from the first bit, and then we're going to substitute e into x squared over 4 and 1 into x squared over 4. And then we have the e squared from the triangle. And doing e squared over 2 minus e squared over 4 plus e squared will give us 5/4 of e squared, and we're subtracting negative 1/4, so that's going to be 5/4 e squared plus 1/4 for the total area of that region R. The question actually states that a and b are rational numbers to be found, so it's quite nice to finish off a question by explicitly stating them. A will be equal to 5 over 4 and b is equal to 1/4. Right, question 14, I think probably the toughest question, or part B is probably the toughest question on the paper, just because it gets quite fiddly. Okay, for A, the number of mice in the population at the start, well, that's telling us that t is 0. So n will be 900 over 3 plus 7 times e to the power of 0. E to the power of 0 is 1, so that will be 7 times 1. So it will be 900 over 3 plus 7, which is 900 over 10. And 900 over 10, we don't need a calculator for that. It means there are 90 mice at the start. Then for B, I considered doing this using the quotient rule. That's absolutely fine. If you've used the quotient rule, you can do it that way. Thought I'd switch it up and use the product rule here. Not entirely sure that's made it easier, but it is an alternative, perfectly legitimate way of doing it. So I'm going to start by differentiating the inside. So the 3 disappears, and we'll times by the minus 0.25. Lots of 7e to the minus 0.25t. And then we'll differentiate the outside. So the minus 1 from the power of the outside is going to come down, and we're going to get minus 1 lots of 3 plus 7e to the minus 0.25t, all to the power of negative 2. The 900 I've just left out the front. Then I've taken the 3 plus 7e to the minus 0.25t to the negative 2. I've taken that to the bottom of the fraction and I've split it into two separate parts. The first part I've given to the 900 at the front. So what I'm writing there is the first one of the 3 plus 7e to the minus 0.25t's. Then we're going to times by, the negatives will cancel, negative 0.25 times negative 1, the minuses cancel, so just a 0.25. We've got the 7e to the minus 0.25t, and all of that is going to go over the second 3 plus 7e to the minus 0.25t's. Okay, so just to save a bit of space, I'm replacing the 900 over 3 plus 7e to the minus 0.25t as n. And then the 0.25 I've taken out as a quarter. And then this is the sort of the fiddly bit, playing about with it. I've put in a plus 3 and then I've added a minus 3 in the numerator. So I've not changed the 7e to the minus 0.25t, I've just added a 3 at the front and a minus 3 at the end. And that allows me to split it up into two separate fractions where some of it will cancel. So we've got an n there. I'm going to take that the first 3 plus 7 lots of e to the minus 0.25t, and take that out as a separate fraction and cancel it immediately just to make 1. And then we're going to subtract the 3 that's left over 3 plus e to the minus 0.25t. All of that's going to be over 4 because we're finding a quarter of it. And then I'm going to multiply the top and the bottom by 300. So the 1 becomes a 300. The 3 that's at the top of the fraction there will become a 900. The denominator of that bit stays the same. And the denominator will become a 1200. So I've multiplied the top and the bottom there by 300. And we can now see that that's in the desired format. I can replace the 900 with 900 over 3 plus 7e to the minus 0.25t. I can replace that as an n, and we'll get n lots of 300 minus n all over 1200 as required. Well done if you managed to work that out. That's not easy. I suspect there are slightly more elegant solutions than the one I've provided here. Do let me know if you found one. My email address is in the channel. For C, the maximum growth rate, we're looking at dn by dt, the expression we now have, that's a negative parabola, so the maximum growth rate is going to be between 0 and 300. It's going to be exactly halfway between 0 and 300, so it's going to be when n is 150. So plugging in 150 into the original equation and multiply both sides by 3 plus 7e to the minus 0.25t, divide both sides by 150, 900 divided by 150 is 6, so subtract 3 from both sides, divide both sides by 7, take natural logs of both sides, and then lastly divide both sides by negative 0.25, or times both sides by minus 4 if you prefer. You get t to be 3.39. And then for part D, the value of P is going to be 300. We can just read that off. Well done if you got that. Good job. All right, bye.